So Mauro, you can share the screen now.
Okay, thank you so much. I'll try to share.
You can share now.
Give me 1 second, because Zoom wants to to get some privileges. Okay, so I will drop the connection and rejoin. Okay, so give me a second. Okay.
Okay, sure. Or চলে কিছু সমস্যা আছে এটা আমাদের
Okay, so I'm back and I'll try to share my screen now.
And this is there.
It's there.
Okay, so sharing. Yes. Okay, so
Yes.
yeah,
You can make it full screen.
sure. Can you see it now? Yeah.
Perfect.
Yes.
Perfect.
Okay. So thanks a lot. Thank you for the opportunity to talk, and thank you for the invitation.
Before you proceed, I will just introduce you to the audience.
Sure. But you record my thanks.
Thank you very much. So now we have Professor Mauro Paternostro from Palermo, University of Palermo. So he is very well known physicist, and he did his PhD from University of Belfast, 2005. And then he has been working. He also got Alexander von Humboldt postdoctoral fellow. So he was that's a very prestigious one. And then also then he continued as a full professor at the University of Palermo. And then he has more than 300 publications, so it's about 19,000 citations. So he's a big person in this field. So I welcome you. Thank you very much for joining with us. So you can start now. Thank you very much.
Thank you so much for the too generous introduction, and many thanks for being there and listening to this talk. So I hope you can hear me all right. Okay, so and please stop me whenever what I'm saying doesn't make any sense. Okay, so I'll be talking of ways to enhance quantum information processing using basically forms of many body interactions that build up neuromorphic approaches to data processing. So this talk will be basically a superposition, in a sense, classical, of quantum computation and machine learning. And in fact, what I'll do is that I will start with a very pedestrian introduction to machine learning for quantum physics, and then we will move to the important bits of the presentation. One part will deal with quantum gate synthesis and design. So we'll see how machine learning will help us designing multipartite quantum gates and their implementation. Then I'll address the problem of state engineering. And again, making use of the tools of machine learning, we will see at least one scheme for the preparation of complex quantum states in large Hilbert spaces. And then that depends on how much I'm going to talk. I'm taking to talk, so I'll make use of a different approach to machine learning, which is called reservoir computing, to address the problem of quantum property validation. So how we can validate the features that characterize a given state, the properties that characterize a given state, bypassing entirely tomography of the state itself. So without further ado, let's start digging into this very declaredly and admittedly bad introduction to machine learning, and I'll do it under the so to say the framework and the motivations provided by three features of quantum state engineering, okay, which can be seen and taken as the good, the bad, and the ugly of quantum state engineering. And I'm going to change them into three different things. The first is the annoying, and that's the time that you need in order to achieve a faithful and high quality state by quantum engineering processes. The bad, which is that typically these processes for synthesizing states and processes cost a lot of money. And then the ugly, which is really the bad part. And the bad part is that although you might, or despite the fact that you might have dedicated a lot of time to quantum state engineering, and you might have spent a lot of money from your grants in arranging the best possible experimental setting that you can afford, given the grant that you have, still you might fail and you might achieve something that is just not good enough. And the plot that you see in this slide, so the bottom right corner of this slide, is a plot taken from a paper by the Matteo Paris group in Milan a few years ago, where these guys were basically showing the performance of engineering entangled state of two modes, okay, two thermal modes, so to say, against the thermal occupation, the inverse temperature of the state itself, so that's beta on the horizontal axis, and the mean number of photons in the state itself, and that's the n in the vertical axis. What they did was showing that although the protocol for the generation and the synthesis of entangled state of initially thermal quantum state, quantum harmonic states, achieved a fidelity of more than 99% with target states, and this is the pink or orange area that you see in this slide. Still, the chances that the protocol could instead achieve with a very high fidelity with the target state, a state that is instead separable, was very large. Okay, so the closeness of the state that they were able to achieve, larger than 99%, was not a guarantee for the achievement of the features in the target state that they wanted to get, despite, say, the number of hours spent in the synthesis and the amount of resources deployed to achieve that. And precisely, say, tackling these three features, no, the annoying, the bad, and the ugly, for quantum state engineering and quantum process engineering, in order to tackle that, I will make use of sort of an exotic approach based on machine learning. In order to make everyone on the same page, put everyone on the same page, let's really go into a very quick explanation of which form of machine learning I mean. Okay, so this blob here, because I just understand things through cartoons, and I'm a stupid person, so I'll try and explain it the way I understand it. Okay, so this blob here is computer science. Okay, and down here in a corner of computer science is artificial intelligence, which is the subfield of computer science that studies intelligent agents. So what are intelligent agents? They are devices that perceive the environment and act so as to maximize the chances that they have to achieve successfully a given goal. Okay, so it's basically the best definition of a politician. No, so you probe the environment around you, and then you adapt your strategy so as to achieve a given task, a given goal. And in a corner of artificial intelligence is machine learning, finding a very, say, a precise or a faithful definition of what machine learning is a very difficult task. So we don't have it formalized in a sense, but very, very roughly speaking, very, very superficially, machine learning seeks patterns in empirical data, but does not enforce a model on the data themselves, okay? So basically what a machine learning approach does, or algorithm does, is that it puts in place a strategy to discern patterns, but through a data-driven approach, not a model-driven approach. You don't have to enforce a model on the data. Patterns are instead derived, they are learned by the algorithm from the data. And they are derived to make sense of previously unknown inputs. The thing that is closest to a proper definition of what machine learning is the sentence taken from a talk by Arthur Samuel. I think it has been then transcribed later on. The talk is from 1950s, more or less, that states that machine learning is a field of study that gives computer the ability to learn without being explicitly programmed. So that gives you the idea of a data-driven rather than model-driven approach. And there is plenty of opportunities that are open from the admixture, from the combination, the synergy of machine learning with topics that are probably some of the topics of your own line of investigation, say from quantum chemistry to quantum material science, statistical mechanics, and quantum information. And that opens definitely new avenues of investigation. So much so that many people now talk about quantum machine learning. It's a terminology that I don't like much because it doesn't mean much to me. On the other hand, what makes sense is the distinction between two different takes on the admixture between machine learning and quantum. One take, one approach, one perspective is that of quantum for quantum. And the other one is that of classical for quantum. What I mean by that is that in the quantum for quantum approach, we aim at least at developing quantum algorithms to solve problems of machine learning, so to enhance machine learning algorithms using genuine quantum advantage. So this is not very different from quantum computation, basically, and the development of quantum algorithms. And in fact, it's as difficult as the development of genuine quantum algorithms. And I have to say that today there isn't much progress in this regard. On the other hand, the classical for quantum approach or perspective uses very well established classical machine learning methods to run quantum problems much more efficiently. And this sort of approach has both, say, fruitful results already. It has been a very successful line of investigation, and I think, this is only my opinion, it will bear more fruits as we go on exploring the interplay between machine learning, AI in general, and quantum science and technology. And this is precisely the context that we are going to explore. So this interplay, this gray zone between quantum information processing and machine learning. And if you are interested in reading more, and I apologize to the experts that are in the audience, but if you are interested in learning more or reading more, this is a not very updated list of references that are instead very, very useful as introductory means to the field. In particular, the book of Peter Wittek is a fantastic introduction to the field and the context. Okay, so how are we going to use this classical for quantum approach that I have advocated for so far when I'm interested in synthesizing, in designing quantum gates? Okay, so before starting, I need to give credit to people that made the problem and the results possible. These are Luca Innocenti in my group in Palermo. He was a PhD student in Belfast when I was there. And Alessandro Ferraro, who used to be in Belfast with me and is now at the University of Milan. And then two key persons are Sugato Bose at University College London, who I believe is a very well-known person in the audience, across the audience, and Leonardo Banchi, University of Florence. So the results are in this paper published in New Journal of Physics a few years ago. And the problem that we were tackling in that paper stemmed from very, very classical motivations, so to say. Okay, so this is Sammy. And this photo is from when he was 3 years old. Sammy is my son, and he's a typical learner. Okay, so Sammy is also interested in Lego bricks. Okay, and in particular, what he wants is to build and what he wanted when he was 3 was to build a pirate ship with Lego bricks. So you can buy a box of specially designed Lego bricks to build the pirate ship, but it's very, very expensive. So Sammy would have to do with what he had at home at the time. And that was only 15 Lego bricks, red, green, yellow, and blue. So Sammy had 15 blocks of this color and these shapes. And the question was, can he build the pirate ship using only the 15 blocks that he had? Let's translate it into, let's translate the problem into something a little bit more meaningful from a mathematical / physical viewpoint. And the question is, can I synthesize exactly a gate G from a generator, an Hamiltonian HG, which is very much likely a many-body Hamiltonian, that comprises operations drawn only from an assigned subset of interactions. Okay, so just to schematize things a little bit more clearly, suppose I want to implement a transformation that I'm schematizing as these, I don't know, is an heptagon, 2, 4, 6, an heptagon, is a red heptagon, okay? So the desired transformation that I want to implement is this red heptagon, that is the pirate ship that Sammy wants to build. But I only want to use these transformations. So I will only have green squares, blue triangles, and red pentagons. These are the 15 Lego bricks that Sammy had at home. Can I arrange these available transformations in a way that I can exactly synthesize the red heptagon that I would like to achieve? Can I arrange the 15 blocks that Sammy has so that I can achieve the pirate ship? The answer is very much likely yes, if I have a large enough set of transformations. But if I only have available the green squares, because maybe my experimentalist friend only can implement a certain set of interaction, would I be able to synthesize the very same gate? So if I take away some of the bricks that Sammy had, can he do it? Can he still implement or realize or build up the pirate ship that he wants? Okay, take-home messages. So from this moment on, you can fall asleep if you want. It's a long day for you. It's already afternoon, so I would not be offended. Don't worry. But the take-home messages will be the possibility. So what we demonstrated was the existence of 3 conditions that allow me to produce a new Hamiltonian, H tilde, that comprises only transformations that have been drawn from the set of allowed operations. Apologies, here there is a pi, while it should be gamma. Gamma is the set of transformations that I'm allowed to use, okay? So apologies for the type. So H tilde comprises only the transformations that I'm allowed to use, and in such a way that the exponentiation of H tilde realizes exactly the gate that I wanted to implement. I will then present a supervised learning-based optimization technique that allows us to train a network of qubits to act in exactly the way I want, in exactly the way I should be implementing in order to achieve G and achieve the desired gate synthesis problem. Okay, so these are the take-home messages. Let's see what is the general methodology that we have put in place. So let's say that my gate G, the transformation that I would like to achieve, is the exponentiation of HG. HG is the generator of gate G. So, and this guy contains, in general, many transformations that I don't say that I should realize, many coupling that I should realize, and that maybe are not allowed. Okay, so the Hamiltonian AG, which I can derive by taking simply say the log of the left-hand side of my gate, my Hamiltonian AG would comprise and contain feasible the green squares and unfeasible transformations. For instance, transformations that I'm schematizing as these red pentagons. I can only use the green squares, I stress and remind you. So what is the goal that I want to achieve? Is the construction of this new Hamiltonian, H tilde, using only green squares. And in such a way that the exponentiation of this Hamiltonian achieves the right transformation, not just for a single preparation of my input, my register, of the input state of my register, but regardless of the input preparation of my register, so for any possible input state, I really want to achieve G, regardless of what is the input that I might be given with. What do I not want? I don't want to achieve control. Okay, so I don't want to have complicated time-dependent Hamiltonians. I don't want to extend my Hilbert space to ancillary system and make my problem even more complicated than what it is already. And I don't want to control the way different qubits in my register interact with each other. So I don't want to implement any complicated quantum control strategy. So it's a very constrained, very contrived scenario that nevertheless can be tackled. And what do we want is that H tilde contains only feasible interactions, so the green squares. One condition, so these are the three conditions that I mentioned before that exist. Another condition that I want to impose is that H tilde commutes with HG, with the true generator of my true gate, my desired gate G. And then, and this is a little bit less intuitive to understand, that the eigenvalues of the difference between H tilde and H, the two generators, not the actual generator and the one that I want to synthesize through only available transformation, is an integer number of times phi. Okay? If I am able to satisfy these three conditions, then I can build an HG tilde that achieves gate G exactly and for any input state to my register. Okay, the first one is a very straightforward condition and is what I'm imposing, so to say. The other two are a little less obvious, but one can. So what I'm asking you is to digest them for now. Okay, if you want the details, you look at the NJP paper where the explanation for these two conditions are given in full glory. What we need at this stage is to simply accept that these two conditions that are not very obvious and in general difficult to achieve can be solved, can be matched analytically for at least some situations of physical interest. And I will give a couple of examples later on. The second thing that I ask you to accept is that when I impose these two conditions, I would be able to identify certain efficient starting point in my numerics that will allow for a successful optimization approach that will lead me directly to the desired HG tilde. And how is the numerics built in order to achieve the H tilde Hamiltonian? Well, what we use is the following. We decompose H tilde over a basis of operators, all drawn from the set of allowed operations. Then I use the second condition, the commutation between H tilde and H, Hg tilde and H, to reduce the number of parameters that appear in the decomposition of Hg, in the parametrization of Hg tilde. This will simplify, in a sense, the structure of my Hamiltonian, of my desired Hamiltonian. Then I impose the third condition, which is the non-trivial step. What I want to impose is that the eigenvalues of the difference in Hamiltonians is an integer number of times pi. And this problem can be mapped into an inverse eigenvalue problem. Now, inverse eigenvalue problems are difficult to solve analytically, and so I solved them using a supervised learning approach. So what we did was to decompose, as I said, my Hamiltonian over the basis of operators drawn from the set gamma. I look at the fidelity between the desired state that I want to achieve for a given input state. And this is the bra of psi upon which G dagger no act. So that is the evolved state of my input state psi according to the desired gate that I want to synthesize. And I compare that to the state that evolved, not the evolved state, through the synthesized Hamiltonian, okay? So the synthesized couple. And I look for the value of the parameters entering this decomposition that achieve fidelity equal to 1 for any input state, regardless of my choice. So it has to work for all input states. What is the algorithm that we use to achieve this fidelity equal to 1 for any input state? We make an initial choice for the parameters of the decomposition. We generate a random set of input states. We run the gradient of fidelity against lambda, no, with respect to lambda, for each of these input states, and we update step by step lambda using momentum gradient. So basically I have two parameters, mu and lambda, that get updated depending on the value of the gradient that I'm taking. Here, I will have to introduce a couple of parameters, one called the momentum term, the other is the learning rate, which I have to keep at bay whenever I implement my learning approach for optimization, and I repeat until fidelity gets a satisfactory value, which is, say, with arbitrary accuracy, close to 1, okay? How do I compute the gradient? I use standard approach based on automatic derivative with error backpropagation. For those of you that are interested in the computational side of these problems, these are packages that are available in Theano, in PyTorch, in TensorFlow, which are standard routines for machine learning. And now we see it in place, okay? We put it in place for the problem of synthesizing a Toffoli gate. Now, I don't need to explain what a Toffoli gate is, a universal quantum gate for a universal gate for quantum computation. Now, the generator of a Toffoli gate is basically a control not gate. The generator of a Toffoli gate is this stuff, right? So it uses a few couplings among the qubits. There are, now if you decompose the product of these operators, you will see that you have single qubit operations. You will see that you have 2 qubit operations, but you have at least one 3 qubit interaction, no? A Z-Z-X interaction. And what I don't want to do, what I don't want is exactly using 3 qubit interactions, because they are difficult to implement in the lab, and 2 qubit terms are very, very natural, much more natural than 3 qubit ones. So my set of allowed transformation is the one consisting of only 2 qubit couplings. So the question is, can I implement this generator of my gate using only 2 qubit couplings So in order to answer, I do what I promised. I decompose my alleged generator, H tilde, over a basis of allowed transformations, allowed couplings. And in this case, what I'm allowing is up to 2-qubit couplings. Okay, so I'm allowing for single qubit, so nothing, needless to say, single qubit coupling, and at most 2-qubit coupling, no 3-qubit interaction at all. I have a number of parameters that enter this decomposition, it's 37 parameters, you trust me, and I reduce this number by using condition 2. I enforce that H tilde Toffoli commutes with H tilde. And by doing that, I reduce the number of parameters all the way to a handful, it's probably 12, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters. So from 37 all the way down to 10 parameters. And now we use this H tilde to run the machine learning approach that I have illustrated. So why do I have to use it? Because 10 parameters is
Mauro,
too
you
big
have so you have 5 minutes to
please.
Yeah, you have 5 minutes left.
That's okay. That's okay. Yeah, that's okay. So I'll just show you the results on the gate synthesis. So in order to solve the problem, this is too large for an inverse eigenvalue problem. So in order to do that, I rely on my machine learning approach. And the results are this. Okay, so this is what my computer outputted. So each line here is a different configuration of parameters, is a different choice of parameters that you can achieve, that you can enforce to your decomposition of Hamiltonian, and that allow you to achieve exactly your generator of a Toffoli gate for any input state. Okay, so for instance, if you follow, I don't know, the red curve, right? So the red curve, each point on this red curve tells you how much each parameter of your decomposition of the Hamiltonian should be in order to get precisely what you say, the Hamiltonian that you needed. Fredkin gate, again, similar problem, no? A controlled swap gate. The Hamiltonian that generates this gate is still requiring at least one 3-body interaction. You want to do it only with 2-qubit terms, and in order to do that, you run the same process once more. You enforce commutation, you reduce the number of parameters, you run the inverse eigenvalue problem on your machine learning approach, and what you get is again a forest of numbers that will allow you to achieve precisely the scope that you had at time. And this plot shows you how the computer optimizes the solution or find the optimal solution in time. So after a transient, it stabilizes, getting the values at the steady state, so to say, of its configuration that then are reported in the rightmost plot. Okay, given that I've spoken too much and for too long, I'll skip directly to the acknowledgement. And these are the guys that put the bread on our table. These are the 2 groups in Belfast and in Palermo that suffer my tantrums. And thank you so much for your attention and your patience. I'm not sure that I can hear you. I think you are. Yeah. Okay.
Yeah, I have to come close to the computer actually.
Oh.
So the talk is open for questions.
I cannot hear any question. Apologies.
So it is like instead of 3-body interaction, and as they are difficult to generalize in experiment, so you restrict it to 2-body interaction. But suppose you have only limited 3-body interaction, but not the generator of this gate. So include even the 2-body, if you include some 3-body, but not exactly what you want. So can the situation be improved further?
I'm sorry, I'm not entirely sure I caught your question. So if you can repeat it, would be great. Can you?
Okay, so the three-body generators, you are restricting to two-body generators. But
That's right.
because it's difficult in experiment to get the three-body generators.
That's
But
right.
suppose you are lucky enough, you have a limited set of three-body generators along with the two-body generators. And then suppose I give you arbitrary gate which needs three-body interaction. So how the
Yes,
situation?
you can do it anyway. So so to say, the examples that I have shown are simply dictated by some form of reasonable expectation, which is that of having only available two-body interactions rather than n-body interaction. But if you have n-body interaction, very much likely your synthesis will be much more economical than what we have with only 2-qubit interaction, but equally effective. So the answer to your question, if I quote it right, is that you can implement your synthesis strategy even with 3-qubit interaction if that's what life gives you.
Yeah, actually, what I'm asking, like any interaction, can you divide in terms of two-body interaction, or you can generate with only two-body interaction with sufficient accuracy?
Okay, this is somehow a different question than the one that we have achieved. Okay, so we are not interested in finding, say, a decomposition of your gate in terms of your n-gate interaction in terms of a small, say, interactions that are only limited to a smaller number of qubits. Or bodies. What we are interested in doing is finding a synthesis of the transformation that you want with only a constrained set of results. So I'm not looking. What I'm not saying is that the decomposition that we have, or the synthesis that we have found is a decomposition in terms of 2-qubit interaction and 1-qubit interaction of your gate. It's not gate decomposition that we are performing. We are synthesizing the generator. So it's a subtle difference, yet an important one.
Yeah. Okay. Thank you. Any other question? Not, then thank the speaker again. Thank you very much.
Thank you so much.
For joining. Yeah.
Thank you very much.
Some time.
Bye. Thank you.
Bye. Thank you.
Not here.
Hi, Utkarsh, can you share your screen? Hello.
Yeah, I can.
Yeah.